Early 1944, Wright Field, Dayton, Ohio. A test pilot steadied his hand on the throttle of the P-51 Mustang as he pushed past the Standard War emergency power setting. The engine roared as boost pressure climbed to 75 in of mercury, fed by a new experimental fuel designated simply as Grade 150. The airspeed indicator swept past numbers that represented the edge of what Allied fighters had previously achieved. At 25,000 feet, the Mustang was accelerating through 448 miles per hour. The test engineers on the ground exchanged glances as the radio crackled with the pilot's report. This was not an incremental improvement. This was a revolution wrapped in purple-dyed aviation gasoline, a chemical advantage so profound that it would render obsolete every assumption the Luftwaffe held about American fighter capabilities. The war in Europe was about to change, and the catalyst was not a new aircraft design or a brilliant tactical innovation, but rather a fuel that allowed existing fighters to perform at levels that defied German expectations. What the Luftwaffe did not yet know was that American and British fuel chemists had achieved something the Third Reich's synthetic fuel program could never match. While German fighters struggled with B-4 fuel rated at 91 octane on the lean mixture scale and their best, C3 fuel barely approached the equivalent of Allied 130 grade fuel. American refineries were producing aviation gasoline with a performance number of 150. The implications were staggering. A P-51 Mustang running on standard 130 grade fuel could reach 437 miles per hour at 25,000 feet. The same aircraft flown by the same pilot at the same altitude running on 150 grade fuel could exceed 448 miles per hour. German fighter pilots who had learned to respect the Mustang's range and high-altitude performance were about to discover that the Americans had fundamentally altered the equation of aerial combat. The Messed Bf-109G, the Luftwaffe's frontline fighter in early 1944, had a maximum speed of 400 miles per hour at altitude. The Fowler-Wolf 190A could reach 408 miles per hour under optimal conditions. Against Mustangs running 130 grade fuel, German pilots could at least attempt engagement on favorable terms. Against Mustangs running 150 grade fuel, German fighters were operating at a fundamental disadvantage that no amount of pilot skill or tactical cunning could overcome. The story of how this advantage came to exist begins not with the war, but with the peacetime work of petroleum chemists who understood that octane rating measured how much an air-fuel mixture could be compressed before spontaneous detonation occurred. Higher compression ratios meant more power from each combustion cycle. More power meant faster aircraft and higher operational ceilings. The science was straightforward, but the engineering required to produce high-octane aviation fuel at industrial scale was extraordinarily complex. In 1940, when the war was already raging in Europe, American aviation fuel production centered on 87-octane gasoline. This was adequate for commercial aviation and early military trainers, but woefully insufficient for high-performance combat. Aircraft. The British, desperate for any advantage against the Luftwaffe's superior numbers, had worked with American oil companies to develop 100-octane fuel, which became available just in time for the Battle of Britain. The difference was immediately apparent. British Spitfires and Hurricanes using 100-octane fuel suddenly had 30 to 40 miles per hour more speed at altitude, and climb rates increased by 500 to 1,000 feet per minute. German pilots who had enjoyed performance advantages with their 91 to 100-octane fuel suddenly found themselves on even terms. The development of 130 grade fuel provided another leap forward. This fuel, with its performance number of 130 on rich mixture settings, became the backbone of Allied air power through 1943. It powered the Merlin engines in both Spitfires and Mustangs, the Allison engines in P-38 Lightnings, and the massive Pratt & Whitney R2-800 radials in P-47 Thunderbolts. Production scaled rapidly under the direction of pioneering aviation fuel advocate General James Doolittle, who had worked tirelessly in the 1930s to convince both the military and oil companies to invest in high-octane fuel development. By 1943, 17 Allied refineries were producing high-octane aviation gasoline using the catalytic cracking process perfected by French immigrant engineer Eugene Houdry. American refineries alone were producing millions of gallons monthly, enough to fuel the massive bomber offensive against Germany and the growing fighter forces that protected those bombers. German fuel production, by contrast, remained bottlenecked by their reliance on synthetic fuel derived from coal. The Burguess process that converted German coal into aviation gasoline was technically sound but slow and resource-intensive. Even at peak production, Germany could produce only a fraction of the high-octane fuel that flowed from American refineries. Most German fighters flew on B-4 fuel rated at approximately 91 octane on the lean mixture scale. Their premium C3 fuel, used primarily in BMW 801-powered Fowler-Wolf 190s and Select Method variants, was roughly equivalent to a light 1130 grade fuel, but available in far more limited quantities. By 1944, perhaps two-thirds of German aviation fuel production was C3 grade, but this still represented only a small fraction of what the Allies were producing. Understanding fuel performance requires grasping a fundamental principle of internal combustion engines. Octane ratings measure detonation resistance. When a piston compresses the air-fuel mixture during the compression stroke, temperature and pressure increase dramatically. If the fuel spontaneously ignites before the spark plug fires, the result is detonation, an uncontrolled explosion rather than a controlled burn. Detonation creates shock waves that damage or destroy engine components. Higher octane ratings mean the fuel can withstand higher compression without detonating. Octane ratings by definition cannot exceed 100 because 100 octane means detonation resistance equivalent to pure isooctane, the reference standard. Performance numbers measure how much better than pure isooctane a fuel can perform. A fuel with a performance number of 150 means it can withstand 50% more compression than pure isooctane before detonating. Creating such a fuel required adding anti-in compounds, primarily tetrathild, and careful blending of aromatic hydrocarbons like toluene and xylene with the base gasoline. British fuel chemists at the Royal Aircraft Establishment tested numerous blends through 1942 and 1943, seeking the optimal combination of anti-no performance, energy content, and manufacturing practicality. American researchers at Wright Field conducted parallel investigations, sharing data with their British counterparts. By early 1943, both nations had produced experimental batches of what they designated as 150 grade fuel. The designation was somewhat misleading because it implied an octane rating of 150, which was chemically impossible. What it actually meant was a fuel with a performance number of 150 on the rich mixture scale combined with 100 octane performance on the lean mixture scale. This fuel, dyed purple for easy identification, underwent extensive testing through 1,943. The results exceeded expectations. Merlin engines running on 150 grade fuel could sustain manifold pressure readings of 75 in of mercury compared to 67 in on 130 grade fuel. This translated directly into increased horsepower. A Packard Merlin FES 1650-7, the engine that powered the P-51 Mustang, generated 1490 horsepower at standard military power on 130 grade fuel. the same engine running on 150 grade fuel at war emergency power. Settings generated 1720 horsepower in the P-51B with its V165-0-3 Merlin variant. The power increase pushed output to approximately 1,600 horsepower. Flight testing at Wright Field confirmed that the performance gains were substantial across all flight regimes. Maximum speed increased by approximately 25 to 30 miles per hour at altitude. Climb rate improved by several hundred feet per minute. Most importantly, these improvements came with no modifications to the aircraft itself. The same Mustang flown one day on 130 grade fuel and the next day on 150 grade fuel became measurably faster and more capable simply because of what flowed through its fuel lines. The decision to introduce 150 grade fuel to operational fighter squadrons was made in early 1944. The timing was carefully considered. The 8th Air Force, based in England and conducting daylight strategic bombing raids deep into Germany, was suffering unsustainable losses. Despite the arrival of the first P-51 Mustangs in December 1943, German fighter forces were still inflicting heavy casualties on American bomber formations. What American planners needed was not just an escort fighter with long range, but an escort fighter so fast that German interceptors could not easily escape or refuse combat on unfavorable terms. In May 1944, the first operational deliveries of 150 grade fuel arrived in England. Distribution was carefully controlled. Not every fighter group received the new fuel immediately. The 8th Air Force began with select squadrons both to manage supply logistics and to evaluate combat performance. The British Royal Air Force, which had pioneered much of the early testing, also began equipping fighter squadrons with the new fuel. Priority went to units tasked with high-speed interception missions, particularly those hunting German V-1 flying bombs that were beginning to terrorize London in June 1944. The V-1 flew at approximately 400 miles per hour at low altitude. Intercepting these weapons required fighter aircraft capable of matching or exceeding that speed at sea level or low altitude where air density reduced the performance of all aircraft. Hawker Tempests and Spitfire 14s could barely catch the V-1 south. Mustangs running standard fuel were marginal. Mustangs running 150 grade fuel had sufficient speed margin to intercept reliably. On June 18, 1944, Major Reed Turner of the 356th Fighter Squadron destroyed a V-1 flying bomb by tipping its wing using his P-51's wingtip, demonstrating a technique that would be used at least 16 times during the campaign. This maneuver required exceptional speed and precision to position the fighters. Wingtip within 6 in of the V-1's wing surface, then use the airflow to roll the flying bomb off course and send it crashing. The first widespread combat use of 150 grade fuel by American P-51 pilots occurred in June 1944, coinciding with the Normandy invasion. Fighter groups of the 8th Air Force, tasked with achieving air superiority over the invasion beaches, flew combat air patrols and bomber escorts using the new fuel. German fighter pilots began reporting encounters with Mustangs that performed beyond what they had previously experienced. Luftwaffe intelligence officers collected pilot reports describing American fighters that could not be caught in any flight regime, that could accelerate away from German interceptors with ease, and that seemed to have power reserves that defied explanation. These reports were initially dismissed as pilot error or exaggeration. German fighter pilots, the intelligence officers reasoned, were tired, outnumbered, and facing mounting losses. Their reports of superior American fighter performance were surely the result of stress and fatigue rather than actual performance increases. This assessment was fundamentally wrong, but the truth would not become clear until after the war. Garrel, a Luftwaffe ace with 275 victories, mostly achieved on the Eastern Front, flew combat missions against American fighters over Germany in 1944. After the war, in interviews conducted during the 1970s and 1980s, R spoke about his encounters with late-war Mustangs. He recalled being shocked at the performance of American fighters during the final year of the war. R, who would later test fly captured American fighters, including the P-51, P-47, and P-38, noted that the Mustang in particular impressed him with its speed, climb capability, and high-altitude performance. What R and other German pilots did not realize during combat was that they were facing an aircraft whose performance had been chemically enhanced beyond its designed specifications, operating at power settings that the original Mustang engineers had never envisioned. The Merlin engine, designed by Rolls-Royce and produced under license by Packard, had been engineered with careful attention to thermal limits bearing loads and detonation margins. Running an engine at higher boost pressures pushed all of these parameters closer to their limits. What made 150-grade fuel revolutionary was that it allowed engines to operate at these extreme settings without the individual revolutionary was that it allowed engines to operate at these extreme settings without the catastrophic detonation that would have destroyed engines running lower-grade fuels at the same boost pressures. The chemistry behind this capability involved the complex interaction of fuel molecules, air molecules, heat, and pressure inside the engine's combustion chamber. Tetrethyl lead, the primary antiox additive, worked by interfering with the chemical chain reactions that led to spontaneous ignition. But there were trade-offs. Tetrethyl lead was toxic, requiring careful handling by ground crews. It left deposits on spark plugs, valves, and cylinder walls, increasing maintenance requirements. 150-grade fuel with its very high lead content accelerated these maintenance issues. Fighter groups using the new fuel experienced more frequent spark plug fouling and increased cylinder wear. American maintenance procedures adapted quickly. Spark plug replacement intervals were shortened. Cylinder inspections became more frequent. Engine overhaul schedules were adjusted. The performance gains were judged worth the increased maintenance burden. For pilots, the transition to 150-grade fuel required new operating procedures. Manifold pressure limits were raised. Pilots had to be careful not to overboost engines, particularly at low altitudes where air density was highest. Most significantly, pilots had to learn to manage fuel consumption. 150-grade fuel provided more power, but running at maximum boost consumed fuel rapidly. Escort missions to Berlin and back already pushed the Mustang's range to its limits. Using the new fuel's full capability meant careful fuel management, knowing when to use maximum power and when to throttle back for cruise efficiency. Combat reports from summer and fall 1944 document the transformation. 8th Air Force fighter groups equipped with the new fuel reported higher victory-to-loss ratios and increased ability to intercept German fighters attempting to attack bomber formations. German fighters that had previously been able to make fast slashing attacks and then escape now found themselves unable to outrun pursuing Mustangs. On August 6, 1944, Lieutenant Hollis Bud Nallin of the 357th Fighter Group, flying as part of Operation Frantic missions to Soviet air bases, encountered German fighters over Eastern Europe. Flying his P-51D named Hellsbells and running 150-grade fuel, Nallin engaged a Miesmid Bf-109 flown by Gottschalk. In the ensuing combat, Nallin's speed advantage proved decisive. He closed rapidly on Schack's aircraft and fired a burst that damaged the German fighter's cooling system. Low on fuel and ammunition after the engagement, Nallin broke off pursuit and waved to the German pilot before returning to escort duties. Schack managed to belly land his crippled aircraft near German lines. For 40 years, Schack wondered why the American pilot had not finished him off, never realizing that Nalin had believed he had merely damaged rather than effectively destroyed the aircraft. When historians later connected the two pilots and arranged a meeting in Germany, Schack acknowledged that the American's Mustang had demonstrated performance that exceeded anything he had previously encountered. The speed with which Nalin had closed and the power reserves evident in the engagement had been unlike previous combats with American fighters. The psychological effect on Luftwaffe pilots was significant. Already outnumbered and facing superior Allied numbers, they now confronted American fighters that seemed to have unlimited performance margins. Their tactical options narrowed dramatically. They could attempt mass attacks, hoping that sheer numbers would overwhelm the escorts. They could refuse combat entirely, preserving their aircraft and pilots. Or they could engage and likely be shot down by Mustangs that were faster, more maneuverable, and flown by American pilots who were growing increasingly confident and aggressive. Reich Marshal Hermann Göring, commander of the Luftwaffe, famously remarked upon seeing P-51 Mustangs over Berlin that he knew the war was lost. This comment reflected the Luftwaffe's strategic dilemma. The Mustang's long range meant that nowhere in Germany was safe from American daylight bombing. The introduction of superior fuel in mid-1944 deepened this crisis. Luftwaffe technical intelligence eventually obtained samples of Allied 150-grade fuel from captured drop tanks or crashed aircraft. German fuel chemists analyzed the samples and confirmed what Luftwaffe pilots had been reporting. The Americans had developed aviation gasoline with performance characteristics beyond anything German synthetic fuel plants could produce. Some German sources suggested that late war C3 fuel approached performance numbers of 150, but production was limited and quality was inconsistent. Allied bombing of German synthetic fuel plants, particularly the raids on Leona and other major facilities in May and June 1944, further constrained German fuel production. By late 1944, the Luftwaffe was rationing fuel. Fighter units received priority, but even they operated under tight constraints. Training for new pilots was cut back severely. Many German pilots reached operational units with minimal flying experience compared to American pilots who typically had several hundred hours of training before entering combat. Between January and May 1944, before widespread introduction of 150-grade fuel, American bombers suffered loss rates of approximately 3 to 6% per mission. These were sustainable but painful losses. Between June and December 1944, after the introduction of 150-grade fuel and the achievement of air superiority, loss rates dropped to under 2% per mission. Fighter victories increased dramatically. American P-51 groups across the 8th, 9th, and 5th 10th Air Forces claimed approximately 4,950. German aircraft destroyed in air-to-air combat between late 1943 and May 1945, with a significant portion of those victories coming after June 1944. The German pilot force, which had entered 1944 with substantial experience despite heavy losses on the Eastern Front, was systematically destroyed. By D-Day on June 6, 1944, only 2 Luftwaffe aircraft appeared over the Normandy beaches. The Luftwaffe still possessed thousands of fighters, but lacked the fuel, the trained pilots, and the tactical flexibility to use them effectively. The technical specifications of 150-grade fuel merit examination. The fuel's lean mixture octane rating of 100 meant it resisted detonation as well as pure ice-octane when engines ran at cruising power settings. The fuel's rich mixture performance number of 150 meant it could withstand 50% more compression than ice-octane when engines ran at maximum power. This combination allowed pilots to cruise efficiently for maximum range, then switch to rich mixtures at high power for combat. Confident that the engine would not detonate even at extreme boost pressures, the handling procedures for 150 grade fuel required special precautions due to the high tetrathyl content. Ground crews wore protective equipment when fueling aircraft. Spills were cleaned up immediately to prevent lead poisoning. Fuel trucks and storage tanks were clearly marked to prevent accidental mixing of fuel grades. Despite these precautions, the safety record was good. Industrial accidents were rare. The transition in operational squadrons required pilot training. Pilots received briefings on the new fuel's properties and updated engine operating procedures. Manifold pressure limits were raised. Operational guidelines specified when and how to use maximum power settings. Aircraft required no modifications. The engines, fuel systems, and all components were compatible with both grades. This compatibility simplified logistics and operations. The production statistics tell a story of industrial mobilization on a scale that Germany could not match. Between May 1944 and April 1945, the 8th Air Force consumed over 53 million gallons of 150 grade fuel. Allied production across all refineries likely exceeded 200 million gallons during operational use. Each gallon required refining infrastructure, chemical additives, including toxic tetraethyled lead, quality control testing, transportation to Europe, storage in secure facilities, and distribution to dozens of airfields. American industrial capacity in 1944 operated at levels that seemed almost miraculous. Factories produced bombers by the thousands, fighters by the tens of thousands. Shipyards launched Liberty ships faster than Germany could sink them. Oil refineries produced aviation gasoline in quantities that exceeded Germany's total fuel production across all grades. This resulted from decades of industrial development, vast natural resources, a protected homeland safe from enemy bombers, and a workforce that included millions of women who took factory jobs to support the war effort. The Royal Air Force used 150 grade fuel extensively in fighter operations over Europe. British squadrons flying Spitfire 14s, Tempest Vs and Mustang 3Es and 4 received priority allocation of the new fuel. RAF pilots reported similar performance improvements to those experienced by American pilots. The Tempest, already one of the fastest piston engine fighters in service, became even more formidable. Tempest squadrons achieved remarkable success against V-1 flying bombs. Between June and September 1944, RAF 150 Wing Tempest shot down 638 flying bombs, with No. 3 Squadron alone claiming 305. Squadron leader Joseph Bry shot down 59 V-1s. Belgian A Squadron leader Remy van Leerde destroyed 44 and Wing Commander Roland Byment destroyed 31. The next most successful interceptors were the Mosquito with 623 victories, Spitfire 14 with 303 and Mustang with 232. The performance margin proved valuable in every role. The combat effectiveness of 150 grade fuel was proven repeatedly through late 1944 and early 1945. Fighter groups that received the new fuel reported increased victory claims and reduced losses. By March 1945, virtually every P-51 unit was running the fuel. Combat reports from this period show overwhelmingly one-sided results. German fighters rarely challenged Allied formations effectively. When they did fight, they usually suffered heavy losses. April 1945, missions over Germany often encountered no aerial opposition. The Luftwaffe was finished, destroyed by attrition, fuel shortages, and the systematic elimination of experienced pilots who could not be replaced. On May 8, 1945, Germany surrendered. The air war over Europe ended with absolute Allied air supremacy. This supremacy had many causes. The P-51 Mustang's long range was crucial. American pilot training was excellent. Allied numerical superiority was overwhelming. But the petroleum engineering advantage that 150 grade fuel provided was significant. The purple-dyed gasoline turned good fighters into exceptional fighters, gave Allied pilots confidence, and represented the accumulated technological and industrial might of nations that could outproduce, out-innovate, and ultimately outlast their opponents. Speed matters in aerial combat. A faster fighter can choose when to engage and when to escape. A faster fighter has tactical flexibility that slower opponents lack. When American fighters became demonstrably faster through the combination of excellent airframe design and superior fuel, the Luftwaffe's tactical options narrowed dramatically. The contrast between German and Allied situations in late 1944 and early 1945 was stark. Allied fighters could fly multiple combat missions daily, limited only by pilot fatigue and aircraft maintenance. German fighters often sat grounded for lack of fuel. When they did fly, they operated under strict fuel conservation measures that limited combat capability. A German pilot who burned too much fuel in combat might not have enough to return to base. An Allied pilot could use full power when needed, confident that adequate fuel reserves existed for the return flight. This operational flexibility had strategic implications. Allied fighters could maintain standing patrols, react to threats aggressively, and sustain operations continuously. German fighters had to pick their moments carefully, conserve fuel rigidly, and often break off combat not because they were losing, but because they were running low on fuel. Luftwaffe pilots flew knowing that every sortie might be their last, not because they might be shot down, but because there might not be fuel for another mission. Allied pilots, by contrast, flew with confidence born from material superiority. They knew their aircraft were fast, their fuel was plentiful, their support system was robust. This confidence translated into more aggressive tactics, better combat results, and higher survival rates. The story of 150 grade fuel is a story about industrial warfare. Victory belonged to the side that could produce not just more aircraft, but better performing aircraft. Not just adequate fuel, but superior fuel. Not just sufficient trained pilots, but an overwhelming surplus of well-trained pilots backed by an industrial base that could replace losses faster than the enemy could inflict them. American and British fuel chemists working in laboratories and refineries never flew combat missions over Germany. They never faced flak or enemy fighters, but their work measured in performance numbers and manifold pressure readings helped decide who controlled the skies over Europe in 1944 and 1945. Every time a P-51 pilot pushed his throttle forward and felt his Mustang surge ahead with power that German fighters could not match. He was benefiting from chemical engineering that transformed crude oil into a fuel that made the exceptional routine. German planners had assumed American fighters would perform within predictable parameters based on aircraft design and standard fuel capabilities. What they encountered instead were fighters whose performance exceeded their calculations, sustained by a fuel production infrastructure so vast and sophisticated that it represented industrial capacity Germany could not counter. By the spring of 1945, as Allied armies overran Germany from east and west, the Luftwaffe had effectively ceased to exist as a coherent fighting force. A few units still flew, often with barely enough fuel for a single sortie. Jet fighters like the Mi-262 represented a technological leap forward, but they came too late and in too few numbers. Handicapped by fuel shortages and the absence of experienced pilots who had been systematically destroyed in combat. The final accounting shows the cumulative effect of Allied advantages. American P-51 groups across all theaters flew hundreds of thousands of fighter sorties. They claimed approximately 4,950 enemy aircraft destroyed in air combat and another 4,131 destroyed on the ground. These numbers represented not just aircraft destroyed, but also pilots killed, experience lost, and German industrial capacity wasted building replacements that were themselves destroyed before achieving strategic effect. 150 grade fuel was not solely responsible for this outcome, but it was a significant contributing factor. It represented the margin of superiority that made the difference between a close fight and a decisive victory. The 448 miles per hour that a properly boosted P-51 could achieve represented not just velocity, but also technological superiority and industrial capacity. This is what German planners had not anticipated: that American fuel chemists and petroleum engineers working far from any battlefield could create a weapon as effective as any gun or bomb. That purple-dyed gasoline could influence aerial combat as surely as superior tactics or better training. That the key to air supremacy over Europe in 1945 would involve the compression ratios of piston engines, the anti-knock properties of aromatic hydrocarbons, and the performance numbers of aviation fuels that exceeded anything Germany could produce. The P-51 Mustangs that flew over Berlin in early 1944 were remarkable aircraft. The P-51 Mustangs that flew over Berlin in early 1945 were the same aircraft, but they were powered by fuel that made them faster, more powerful, and more effective. That difference, measured in octane numbers and performance ratings, in manifold pressure readings and airspeed indicators, was one of the many differences that decided who would win the war for Europe's skies. In that decision lay the fate of Nazi Germany and the demonstration of Allied industrial might expressed as a purple. Liquid pumped into fuel tanks, burned in powerful engines, and transformed into victory one combat mission at a time.